Subscribe to the channel so you don't miss out on any of these videos. Black holes are one of the most mysterious phenomena in the universe. And just when we thought they couldn't get more puzzling, Stephen Hawking flipped everything we knew on its head. Imagine this, an object so dense, so powerful, that nothing, not even light, can escape it. For decades, black holes seemed like the ultimate cosmic trap, a place where the rules of physics break down and information disappears forever. But then, Hawking proposed something groundbreaking. Black holes don't just trap everything forever. They can, in fact, leak. Slowly, over an unimaginable time span, black holes evaporate. Yes, evaporate. How does something so massive, so seemingly eternal, just fade away into nothing? That's the mystery of Hawking radiation. Now, if this concept sounds like science fiction, you're not alone in thinking that. When Hawking first introduced the idea in the 1970s, it was met with skepticism. But the deeper we dive into the science, the more we realize how revolutionary and game-changing this idea really is. And today, we're going to unravel the intricate threads of Hawking's theory, piece by piece. What is Hawking radiation? How does it work? And what does it mean for the fate of black holes, the universe, and our understanding of physics itself? Let's start with the basics. A black hole forms when a massive star collapses under its own gravity. This collapse creates a singularity, a point of infinite density, and around it, an event horizon, the point of no return. Anything crossing this boundary is gone, swallowed by the black hole, never to return. Or so we thought. According to classical physics, black holes are one-way streets. But quantum mechanics, the branch of science that deals with the weird and tiny world of particles, suggests otherwise. Hawking's genius was in combining these two seemingly contradictory ideas, classical physics and quantum mechanics, to show that black holes are not as closed off as we once believed. Here's where it gets wild. Around the event horizon, the boundary of a black hole, the vacuum of space isn't truly empty. Instead, it's teeming with activity. According to quantum mechanics, particles and antiparticles are constantly popping into existence in pairs, only to annihilate each other almost instantly. This happens everywhere in the universe, but near the event horizon of a black hole, something unusual can occur. If one of these particles falls into the black hole while the other escapes, the balance is broken. The particle that escapes carries energy away from the black hole, and this energy loss manifests as radiation, what we now call Hawking radiation. The implications of this are enormous. For starters, it means black holes aren't entirely black. They glow faintly, emitting this radiation over time. And as they emit energy, they lose mass. Over incredibly long periods, this process causes black holes to shrink. Eventually, they evaporate entirely, disappearing into nothingness. This challenges the long-held belief that black holes are eternal. They have lifespans, albeit ones that stretch over billions or even trillions of years. To understand why this is so groundbreaking, we need to consider what it means for the laws of physics. One of the biggest mysteries in science is what happens to information that falls into a black hole. Does it disappear forever? According to classical physics, yes. But quantum mechanics tells us that information cannot be destroyed. Hawking radiation offers a potential solution to this paradox, suggesting that the information might not be lost but instead encoded in the radiation emitted by the black hole. This idea has sparked decades of debate and research, with physicists working tirelessly to uncover the truth. And let's not forget the sheer audacity of Hawking's claim. At the time, the very idea that black holes could emit radiation seemed absurd. After all, black holes are defined by their ability to trap everything, including light. But Hawking's calculations, grounded in the principles of quantum mechanics, showed otherwise. This wasn't just theoretical hand-waving. It was hard math, backed by the rigorous logic of science. Now, if you're wondering what all of this means for the universe, buckle up, because it's a lot to take in. First, let's consider the long-term fate of black holes. The largest black holes, those millions or billions of times the mass of our Sun, will take an unfathomable amount of time to evaporate. We're talking about timeframes so vast that they make the age of the universe look like a blink of an eye. But eventually, even these cosmic giants will shrink down, releasing their energy back into the universe. In a way, it's like the black hole is giving back what it took, spreading its energy throughout space. But there's another layer to this mystery. If black holes evaporate and disappear, what happens to the singularity at their core? Does it vanish along with the black hole? Or does it leave behind some remnant, some trace of its existence? These are questions that remain unanswered, fueling ongoing research and speculation. To grasp the full scope of Hawking radiation, we also need to dive deeper into the mechanics of how it works. Imagine the event horizon as a sort of membrane where quantum effects come into play. Particles and antiparticles are born in pairs, as we mentioned earlier. Near the event horizon, the immense gravitational pull of the black hole can separate these pairs. The particle with negative energy falls into the black hole, effectively reducing its mass. The other particle escapes, becoming part of the radiation emitted by the black hole. What's mind-blowing is how this process is driven by the laws of quantum mechanics, a realm where particles behave more like waves, probabilities blur into reality, and nothing is quite as it seems. Hawking radiation represents a bridge between quantum mechanics and general relativity, two pillars of modern physics that often seem at odds. Hawking's work suggests that these two frameworks, despite their differences, are deeply interconnected. And while we don't yet have a unified theory that fully reconciles them, Hawking radiation is a tantalizing hint that such a theory might one day be within reach. Even beyond its scientific implications, Hawking radiation has captured the imagination of scientists and the public alike. It challenges our perceptions of black holes as ultimate cosmic traps and forces us to rethink what we know about the universe. It also raises profound questions about the nature of time, space, and existence itself. Hawking radiation opens a door to questions about the ultimate destiny of the universe. Black holes are often considered to be the endpoints of stellar evolution, cosmic dustbins where matter is devoured and locked away forever. But if they evaporate over time, it suggests that even the darkest corners of the cosmos are part of a grand cycle of energy transformation. Nothing is truly permanent, not even black holes. This realization fundamentally changes how we view the universe's long-term evolution. One particularly fascinating aspect of this theory lies in its implications for entropy. Black holes are famously associated with entropy, a measure of disorder or information in a system. In the 1970s, physicist Jacob Bekenstein proposed that the surface area of a black hole's event horizon is proportional to its entropy. Hawking radiation confirmed this idea, showing that as a black hole loses mass and shrinks, its surface area decreases, along with its entropy. This ties black holes directly to the second law of thermodynamics, which states that entropy in a closed system must always increase. But here's the twist. Hawking radiation ensures that the total entropy of the universe increases, even as the black hole's entropy decreases. It's a fascinating balancing act that aligns the strange physics of black holes with the fundamental principles of thermodynamics. Now, let's take a closer look at the timescales involved in this process, because they're almost impossible to grasp. For a black hole to completely evaporate through Hawking radiation, it takes a staggering amount of time. Small black holes, with masses equivalent to a mountain, would evaporate relatively quickly by cosmic standards, perhaps within a few billion years. But supermassive black holes, like the ones at the centers of galaxies, take much, much longer. The evaporation process is so slow that, for all practical purposes, we'll never witness it firsthand. Even as the universe ages and stars burn out, leaving behind a cold, dark cosmos, black holes will persist. Only in the unimaginably distant future, trillions upon trillions of years from now, will these giants finally fade away, releasing their last remnants of energy. As black holes evaporate, they transition through different phases. Early on, the radiation they emit is incredibly faint, almost imperceptible. But as the black hole loses mass, the intensity of the radiation increases. Toward the end of its life, a black hole's evaporation accelerates dramatically. The smaller it gets, the faster it radiates energy. In its final moments, the black hole could release an enormous burst of energy before vanishing completely. This death flash, while purely theoretical at this point, is a captivating idea. It suggests that even the demise of a black hole could be marked by a dramatic event, a last gasp that leaves an indelible mark on the surrounding space. But here's where things get even more intriguing. What happens to the information that falls into a black hole? This question is at the heart of one of the biggest debates in modern physics, the black hole information paradox. According to quantum mechanics, information cannot be destroyed. Yet, when matter and energy fall into a black hole, it seems like the information about their original state is lost forever. If the black hole eventually evaporates, does this information reemerge in some form, encoded in the Hawking radiation? Or is it lost permanently, violating the laws of quantum mechanics? Hawking initially believed that information was destroyed in black holes, but this view faced significant pushback from other physicists. Over time, Hawking himself revised his stance, suggesting that information might escape black holes after all, though the exact mechanism remains unclear. Some theories propose that the information is encoded in the event horizon, while others suggest it could be stored in the quantum states of the emitted radiation. Resolving this paradox is one of the greatest challenges in theoretical physics today, and it has profound implications for our understanding of reality. Let's also consider the philosophical implications of Hawking radiation. The idea that something as massive and seemingly eternal as a black hole can evaporate challenges our notions of permanence and stability in the universe. It forces us to confront the reality that even the most enduring structures are subject to change and decay. This is a humbling reminder of the impermanence of all things, from the smallest particles to the largest cosmic entities. It's a concept that resonates deeply, not just with scientists, but with anyone who contemplates the nature of existence. Hawking radiation also highlights the power of theoretical physics to reveal hidden truths about the universe. Hawking didn't observe this radiation directly, no one has. Instead, he derived it through a combination of mathematics and logic, blending quantum mechanics and general relativity in a way that had never been done before. His work exemplifies how human ingenuity can pierce the veil of the unknown, uncovering phenomena that might otherwise remain forever hidden. As we continue to explore the universe, the study of Hawking radiation serves as a beacon, guiding us toward deeper understanding. It raises questions about the unification of physics, the nature of information, and the ultimate fate of the cosmos. These are questions that don't just challenge our intellect. They ignite our curiosity and inspire us to keep searching for answers. And the search is far from over. Physicists are still grappling with the implications of Hawking's work, developing new theories and conducting experiments to test its predictions. One day, we might even find direct evidence of Hawking radiation, perhaps by observing the faint glow of a small black hole in our galaxy. Such a discovery would be a monumental achievement, confirming one of the most revolutionary ideas in modern science. For now, Hawking radiation remains a theoretical marvel, a testament to the power of human thought and imagination. It reminds us that the universe is far stranger and more fascinating than we can ever fully comprehend. And yet, with each new discovery, we inch closer to unlocking its deepest secrets. The concept of Hawking radiation has also opened up a realm of thought experiments and speculative ideas about the universe. One such idea is the potential use of black holes as sources of energy. If a black hole emits radiation, could we one day harness that energy for practical use? This might sound like science fiction, but the principles behind it are grounded in real physics. For instance, a small, artificially created black hole could theoretically radiate enough energy to power entire civilizations. Such a concept, while far beyond our current technological capabilities, underscores how Hawking's work could shape our long-term vision of advanced energy solutions. But there's another layer to consider: the relationship between Hawking radiation and the nature of spacetime itself. Black holes are regions where spacetime is warped to an extreme degree, and Hawking's calculations suggest that this warping is not static. Instead, it's dynamic, with quantum fluctuations constantly bubbling away at the event horizon. These fluctuations are a reminder that even in the seemingly empty void of space, the quantum world is alive with activity. This realization brings us closer to understanding the intricate interplay between quantum mechanics and general relativity, two frameworks of physics that are, as of now, not fully reconciled. Another profound implication of Hawking radiation is its potential role in the grand narrative of the universe's endgame. Cosmologists often discuss the ultimate fate of the universe, with scenarios ranging from heat death to a big crunch. Hawking's work suggests that black holes, which many once thought to be eternal, are not immune to the inexorable passage of time. If black holes evaporate completely, they could significantly influence the distribution of matter and energy in the universe. Over unimaginably long timescales, Hawking radiation ensures that no structure, no matter how massive or enduring, can escape the gradual dissipation of energy. This raises an even more speculative question: what happens in the final moments of the last black hole? As the universe ages into what physicists call the black hole era, where most other structures have decayed or dispersed, black holes will dominate. But even these giants will eventually succumb to Hawking radiation, leaving behind a universe of sparse particles and low-energy radiation. The complete evaporation of the last black hole marks a pivotal moment in the cosmos, a shift from a universe rich in structure and activity to one that is eerily quiet and still. The philosophical weight of this idea is immense. It challenges us to think about the nature of time, the permanence of matter, and the ultimate meaning of existence. If everything in the universe is destined to fade away, what does that say about the significance of our actions, our discoveries, and our understanding of reality? These are questions that stretch beyond science, touching on the deepest aspects of human thought and reflection. To further explore the implications of Hawking radiation, consider its relationship to quantum mechanics. One of the most intriguing aspects of Hawking's theory is how it bridges the gap between the macroscopic world of general relativity and the microscopic realm of quantum physics. Black holes are governed by Einstein's equations of relativity, which describe how gravity shapes spacetime. But Hawking radiation arises from quantum effects at the event horizon, where particles and antiparticles interact in ways that defy classical intuition. This interplay between the two domains offers a tantalizing glimpse of what a unified theory of physics might look like. Hawking's work has also inspired new avenues of research in string theory and quantum gravity. These fields aim to explain the fundamental nature of reality, and black holes serve as natural laboratories for testing these ideas. For example, some researchers propose that black holes are holographic entities, encoding information about the three-dimensional universe in 2 dimensions. This idea, known as the holographic principle, could help resolve the black hole information paradox by suggesting that no information is truly lost, it's just stored in a different form. The study of Hawking radiation also pushes us to consider the limits of observation. Black holes are notoriously difficult to study directly, given their immense distances and the fact that their event horizons prevent light from escaping. Detecting Hawking radiation would require incredibly sensitive instruments capable of identifying faint emissions against the background noise of the universe. Current technology isn't up to the task, but future advancements in observational astronomy and quantum detectors might one day bring this phenomenon within our reach. Meanwhile, scientists are using indirect methods to explore Hawking's ideas. For instance, laboratory experiments with analog black holes, systems that mimic the behavior of black holes using sound waves or other phenomena, have provided preliminary evidence supporting the existence of Hawking-like radiation. These experiments can't replicate the full complexity of a real black hole, but they offer valuable insights into the quantum processes that drive Hawking radiation. Such work exemplifies the ingenuity of modern science, where creative approaches can illuminate even the most elusive concepts. The implications of Hawking radiation extend far beyond black holes themselves. They touch on the very foundations of physics, challenging us to rethink concepts like time, energy, and causality. They also remind us of the interconnectedness of the universe, where phenomena on the smallest scales, like quantum fluctuations, can influence the behavior of the most massive objects in existence. In the grand tapestry of scientific discovery, Hawking radiation is a thread that connects seemingly disparate ideas into a coherent narrative. It demonstrates how curiosity and rigorous thought can unlock profound truths about the universe. And while there's still much we don't know, Hawking's legacy inspires us to keep asking questions, to keep probing the mysteries of existence, and to embrace the wonder of the unknown. Hawking radiation also raises profound questions about the nature of information in the universe. At the heart of this debate lies the black hole information paradox, one of the most contentious issues in theoretical physics. When an object falls into a black hole, the information about its physical state, its mass, charge, and other quantum properties, seemingly disappears beyond the event horizon. But quantum mechanics dictates that information can never be destroyed. Hawking's work, suggesting that black holes emit radiation and eventually evaporate, adds a perplexing twist to this paradox. If the black hole disappears completely, does the information it once contained vanish as well, or is it somehow preserved? This dilemma has sparked decades of debate among physicists. Some argue that the information is encoded in the Hawking radiation itself, though in a form so scrambled it's effectively inaccessible. Others propose that the information remains imprinted on the event horizon, a concept linked to the holographic principle. This principle posits that all the information about a three-dimensional object can be encoded on its two-dimensional boundary. If true, it suggests that black holes act as cosmic holograms, preserving the details of everything they consume in a way that aligns with quantum mechanics. Another idea, more speculative but equally fascinating, involves the possibility of wormholes or hidden dimensions acting as conduits for information. Could information falling into a black hole be transported elsewhere in the universe or even into another universe entirely? While these ideas remain untested, they highlight the innovative thinking that Hawking radiation has inspired. The implications of the information paradox extend far beyond black holes. They challenge our understanding of the laws of physics and suggest that the universe may operate in ways that are fundamentally different from what we perceive. Resolving this paradox could provide the key to unifying general relativity and quantum mechanics, the two pillars of modern physics that have long resisted integration. A successful theory of quantum gravity, which merges these frameworks, would revolutionize our comprehension of the cosmos. Hawking's contributions don't stop at his theoretical work. His ideas have influenced generations of scientists, inspiring new approaches to understanding black holes and their place in the universe. For example, recent discoveries, such as the imaging of a black hole's event horizon using the Event Horizon Telescope, have brought us closer to confirming some of the predictions made by Hawking and his contemporaries. While these images don't directly show Hawking radiation, they provide critical data about the behavior of matter and energy near black holes, laying the groundwork for future discoveries. The potential for detecting Hawking radiation also brings us into the realm of advanced technological possibilities. Imagine a future where we can study black holes in detail using instruments capable of capturing the faint signals of radiation they emit. Such breakthroughs would require innovations in quantum computing, astrophysical observation, and data analysis on an unprecedented scale. But the rewards would be immense. Not only would we gain empirical evidence for Hawking's theory, but we would also unlock a deeper understanding of the universe's most enigmatic phenomena. This pursuit ties into humanity's enduring fascination with black holes. These objects are not just scientific curiosities. They're also symbols of mystery, power, and the unknown. They represent the limits of human understanding, pushing us to confront the boundaries of knowledge and imagination. Hawking radiation, as an idea, captures this spirit perfectly. It's a reminder that even in the darkest corners of the universe, there is light, or at least radiation, hinting at the secrets waiting to be unveiled. Another angle to consider is how Hawking's theory relates to the origins of the universe itself. The Big Bang, which marks the beginning of time and space as we know it, also involved conditions of extreme density and temperature. In many ways, the singularity at the start of the universe mirrors the singularity at the center of a black hole. Could the processes that govern black holes also shed light on the birth of the cosmos? Some physicists speculate that studying Hawking radiation and black hole mechanics might reveal insights into the quantum fluctuations that triggered the Big Bang. This connection between black holes and the early universe also extends to the concept of inflation, a rapid expansion of space immediately after the Big Bang. During this period, tiny quantum fluctuations were stretched across vast distances, seeding the structures of galaxies and clusters we see today. These fluctuations, governed by quantum mechanics, may be related to the same processes that generate Hawking radiation. By exploring these links, scientists hope to build a more complete picture of the universe's origins and evolution. As our understanding of Hawking radiation deepens, it's likely to intersect with other cutting-edge areas of research, such as dark matter and dark energy. These mysterious components make up the vast majority of the universe, yet remain largely unexplained. Some theorists propose that black holes and their interactions with Hawking radiation could offer clues about the nature of these phenomena. For instance, could the evaporation of primordial black holes, those formed in the early moments of the universe, be responsible for some of the unexplained signals we detect in cosmic observations? The idea of primordial black holes ties back into the longevity and scope of Hawking's insights. These tiny, ancient black holes would emit radiation at a much faster rate than their larger counterparts, potentially leaving detectable traces in the universe today. Searching for these signals is an active area of research, with scientists examining everything from high-energy cosmic rays to unusual patterns in the cosmic microwave background. Each of these efforts builds on the foundation laid by Hawking's groundbreaking theory. Hawking radiation also has implications for the concept of multiverses, a collection of universes beyond our own. If black holes act as bridges to other universes, as some speculative theories suggest, then their evaporation could play a role in how energy and information transfer between these realms. While these ideas remain in the realm of conjecture, they highlight how Hawking's work continues to inspire bold thinking and new hypotheses about the cosmos. Through all of this, one thing becomes clear: the story of Hawking radiation is far from over. It's a living, evolving narrative that continues to challenge, intrigue, and inspire scientists and enthusiasts alike. Each new discovery adds another layer of complexity, drawing us ever closer to understanding the true nature of reality. The deeper we delve into Hawking radiation, the more profound its implications become, not just for black holes, but for the fabric of the universe itself. One particularly intriguing aspect is how this theory ties into entropy and the arrow of time. Entropy, a measure of disorder, is a cornerstone of thermodynamics and plays a key role in our understanding of the universe. Black holes, as immense objects that consume matter and energy, were once thought to reduce entropy by locking away information. However, Hawking radiation flips this idea on its head. Stephen Hawking demonstrated that black holes emit radiation, and in doing so, they lose mass and energy. This process increases entropy in the universe, adhering to the second law of thermodynamics, which states that entropy must always increase. Essentially, black holes are not cosmic dead ends, they are engines of entropy production. This discovery has profound implications for our understanding of time itself. Since the arrow of time is intrinsically linked to the increase of entropy, Hawking's theory suggests that even black holes follow the same temporal rules as the rest of the universe. What's even more fascinating is how this ties into the eventual fate of black holes. As they radiate energy and lose mass, they slowly shrink and grow hotter. This increase in temperature accelerates the rate of radiation, creating a feedback loop that leads to their eventual evaporation. The final stages of a black hole's life are theorized to be extraordinarily energetic, releasing a burst of radiation as the black hole disappears completely. This process could leave behind a residue of particles or, as some theories suggest, a naked singularity, a point where the laws of physics as we know them break down entirely. This theoretical endpoint of black hole evaporation is a tantalizing puzzle for physicists. If Hawking radiation leads to the complete disappearance of a black hole, what happens to the singularity at its core? Does it dissolve into the surrounding space-time, or does it create a new kind of structure we have yet to observe? Some propose that the final burst of radiation could carry the information once contained within the black hole, albeit in a form that might be irretrievably scrambled. Others suggest that the information could be preserved in a way we have yet to understand, possibly encoded in the quantum properties of the emitted particles. This brings us back to the question of information loss and its implications for quantum mechanics. One of the core principles of quantum theory is that information about a system's initial state must always be preserved. If black holes can destroy information, as the classical interpretation of Hawking radiation might imply, this principle would be violated. Resolving this conflict is one of the greatest challenges in modern physics and has led to several groundbreaking ideas. One of the most promising approaches is the concept of black hole complementarity. This hypothesis suggests that information is simultaneously both inside and outside the black hole, depending on the perspective of the observer. From outside the event horizon, the information appears to be encoded in the radiation emitted by the black hole. From within, it might be preserved in some as yet unknown manner. This duality aligns with the principles of quantum mechanics, where particles can exist in multiple states until observed. Another avenue of exploration is the holographic principle, which posits that all the information within a volume of space can be represented on its boundary. Applied to black holes, this means that everything consumed by the black hole might be encoded on its event horizon. If true, this could provide a way to reconcile Hawking radiation with the laws of quantum mechanics. The holographic principle also has far-reaching implications for our understanding of the universe, suggesting that our three-dimensional reality might itself be a projection of information encoded on a distant, two-dimensional boundary. The quest to fully understand Hawking radiation and its implications is driving advancements in both theoretical and experimental physics. On the theoretical side, efforts to develop a theory of quantum gravity aim to bridge the gap between general relativity and quantum mechanics. Such a theory could provide the tools needed to unravel the mysteries of black holes and their radiation. On the experimental side, physicists are searching for ways to detect Hawking radiation directly. While the radiation from astronomical black holes is too faint to observe with current technology, experiments with analog black holes in laboratory settings have shown promise. Analog black holes are systems that mimic the behavior of black holes using sound waves, light, or other phenomena. For example, physicists have created setups where waves propagate through a medium with a velocity gradient, creating a horizon-like effect. In these experiments, researchers have observed behavior analogous to Hawking radiation, providing indirect evidence that the phenomenon is real. These experiments are invaluable, not just for testing Hawking's theory, but also for refining our understanding of quantum mechanics and the nature of space-time. The search for Hawking radiation in the cosmos also continues. Astronomers are investigating high-energy events and cosmic phenomena for potential signatures of evaporating black holes. Primordial black holes, in particular, are a focus of interest. These hypothetical black holes, formed in the early universe, would be small enough to have evaporated partially or completely by now, potentially leaving detectable traces. Observing such an event would provide groundbreaking evidence for Hawking's theory and open new windows into the early universe. As we uncover more about Hawking radiation, it becomes increasingly clear that black holes are not the isolated, insatiable entities we once thought they were. Instead, they are dynamic, evolving structures that interact with the universe in complex and fascinating ways. They are not just destroyers but also creators, contributing to the entropy and energy balance of the cosmos. They challenge our understanding of fundamental physics, pushing us to rethink long-held assumptions and explore new ideas. In many ways, Hawking radiation serves as a bridge between the infinitely large and the infinitesimally small. It connects the vastness of black holes with the quantum mechanics that govern particles at the tiniest scales. By studying this phenomenon, we are not just learning about black holes, we are also probing the fundamental nature of reality itself. It's a journey that has already transformed our understanding of the universe and promises to continue doing so for generations to come. The implications of Hawking radiation stretch far beyond black holes, touching on some of the most profound questions about the universe. One of the most significant ideas it introduces is the concept of a finite lifespan for black holes. Previously thought to be eternal objects, black holes were considered unchanging fixtures of the cosmos, growing only by consuming matter. But Hawking's revelation that they emit radiation and lose mass over time fundamentally alters this perception. To grasp the enormity of this discovery, consider the timescale involved. The rate at which a black hole emits Hawking radiation is inversely proportional to its mass. Larger black holes, with masses millions or billions of times that of the Sun, emit radiation at an almost negligible rate. It would take longer than the current age of the universe, trillions upon trillions of years, for these black holes to evaporate completely. Smaller black holes, however, radiate faster and would evaporate more quickly. This spectrum of lifespans suggests that the universe, in its most distant future, will experience the gradual extinction of black holes. This process of evaporation paints a hauntingly beautiful picture of the far future of the universe, often referred to as the black hole era. In this epoch, long after stars have burned out and galaxies have dispersed, black holes will remain as the final vestiges of structure in the cosmos. They will continue to radiate energy, slowly losing mass and contributing to the faint background of thermal energy in the universe. Over unimaginable timescales, even the largest black holes will reach their final moments, disappearing in a blaze of Hawking radiation. This signals the transition to the dark era, a time when the universe consists of a thin, diffuse soup of particles, with no complex structures remaining. The ultimate fate of the information contained within black holes during their evaporation is one of the most puzzling aspects of Hawking radiation. This is not just an academic question, it strikes at the heart of our understanding of physics. If the information about the matter consumed by a black hole is lost forever, it creates a paradox that challenges the foundations of quantum mechanics. This is known as the black hole information paradox, and resolving it is one of the most important goals in modern physics. One proposed resolution to the paradox involves the idea that information is not lost but rather encoded in the radiation emitted by the black hole. This hypothesis suggests that as a black hole radiates, the particles it emits carry subtle quantum imprints of the information contained within the black hole. However, the mechanism by which this information might be preserved and decoded remains elusive. The emitted radiation appears thermal and random, which poses significant challenges to recovering specific information. Another fascinating approach to the paradox comes from string theory, a theoretical framework that attempts to unify general relativity and quantum mechanics. In string theory, black holes are described not as singularities but as complex, multidimensional structures with finite sizes. This perspective opens up new possibilities for understanding how information might be stored and released during the evaporation process. Some researchers propose that string theory's mathematical tools could provide a way to describe the intricate quantum states of black holes, potentially offering a solution to the paradox. Recent developments in theoretical physics have also brought renewed attention to the holographic principle. This idea, rooted in string theory, suggests that all the information within a region of space can be described by a theory operating on its boundary. Applied to black holes, this principle implies that the information about everything consumed by a black hole might be encoded on its event horizon. This perspective aligns with Hawking's work and could provide a framework for reconciling the apparent loss of information with the laws of quantum mechanics. The implications of Hawking radiation for the nature of space-time are equally profound. Black holes are regions where gravity is so intense that the curvature of space-time becomes extreme. The discovery that black holes can emit radiation suggests that even these regions are not beyond the influence of quantum mechanics. This insight has fueled efforts to develop a theory of quantum gravity, which would unify the general theory of relativity with quantum mechanics. A complete theory of quantum gravity could revolutionize our understanding of the universe, providing answers to questions about the nature of space, time, and the fundamental forces. It could also shed light on what happens at the singularity of a black hole, a point where the equations of general relativity break down. Understanding singularities is crucial for deciphering the ultimate fate of black holes and their role in the cosmos. The study of Hawking radiation has also inspired experimental efforts to probe the behavior of black holes and their analogues. While it is currently impossible to observe Hawking radiation directly from astronomical black holes, researchers have created laboratory experiments that simulate similar phenomena. For example, experiments using Bose-Einstein condensates, a state of matter where particles behave collectively as a single quantum entity, have produced effects analogous to Hawking radiation. These experiments provide valuable insights into the theoretical predictions and help refine our understanding of the underlying physics. Another exciting avenue of research involves searching for primordial black holes. These hypothetical black holes, formed in the earliest moments of the universe, would have masses much smaller than those of stellar black holes. If they exist, some of these primordial black holes might be small enough to have evaporated significantly or completely by now. Observing the remnants of such evaporation, such as high-energy particle bursts, could provide direct evidence for Hawking radiation. Primordial black holes are also of interest for their potential role in explaining dark matter, the mysterious substance that makes up most of the universe's mass. If primordial black holes are abundant enough, they could account for a significant portion of dark matter. Studying these objects could therefore address multiple cosmic mysteries at once, providing insights into both black hole physics and the nature of dark matter. As our understanding of Hawking radiation deepens, it becomes increasingly clear that black holes are not just cosmic enigmas but key players in the story of the universe. They challenge our assumptions about the nature of reality, forcing us to confront the limits of our knowledge and the possibilities beyond. Whether through theoretical breakthroughs or experimental discoveries, the quest to unravel the mysteries of Hawking radiation promises to reshape our understanding of the cosmos. The story of Hawking radiation is a testament to the power of human curiosity and ingenuity. From Stephen Hawking's groundbreaking insights to the ongoing efforts of physicists around the world, it reflects the unrelenting drive to explore the unknown. As we continue to push the boundaries of what we know, we are reminded that the universe is a vast, complex, and endlessly fascinating place, with mysteries waiting to be uncovered. The journey of understanding Hawking radiation is far from over, and as we continue to delve deeper into the nature of black holes, we will likely uncover even more unexpected surprises. One of the most exciting aspects of this discovery is how it has spurred new theories, experiments, and philosophical discussions about the fabric of the universe. As Hawking's radiation theory intertwines with the study of quantum mechanics, general relativity, and cosmology, it becomes increasingly clear that the questions posed by black holes, once considered theoretical curiosities, are inextricably linked to the fundamental workings of space, time, and matter itself. As we venture further into the implications of Hawking radiation, it is essential to explore the relationship between black holes and entropy, which brings us closer to understanding the eventual fate of information and the nature of our universe's evolution. Entropy, in its simplest form, is a measure of disorder or randomness. In classical thermodynamics, systems naturally evolve from a state of low entropy, order, to a state of high entropy, disorder. This idea of increasing entropy governs everything from the movement of molecules to the ultimate decay of stars and galaxies. However, when applied to black holes, entropy takes on a deeper, more complex role. Hawking's radiation is not only a product of quantum mechanics, but it also has thermodynamic implications. In his theory, the black hole's event horizon, the boundary beyond which nothing can escape, is associated with entropy. This entropy is proportional to the area of the event horizon, not the volume of the black hole, as you might intuitively expect. This insight gave rise to what is now known as the Bekenstein-Hawking entropy, named after physicists Jacob Bekenstein and Stephen Hawking, who jointly developed this idea. The concept of black hole entropy is critical because it challenges our understanding of the second law of thermodynamics, which states that entropy always increases in an isolated system. If a black hole evaporates through Hawking radiation, how does the entropy behave? The answer, in part, lies in the way that the emitted radiation carries away the black hole's mass and entropy. As the black hole loses mass, it also loses entropy, and eventually, the black hole will disappear entirely, leaving behind nothing but radiation. This process forces us to reconsider the role of black holes in the cosmic thermodynamic balance and the ultimate fate of information. The relationship between black holes and entropy also plays a role in the black hole information paradox. The paradox stems from the apparent contradiction between the principles of quantum mechanics and the behavior of black holes. Quantum mechanics dictates that information about a system's state cannot be lost, while general relativity suggests that once matter falls into a black hole, it is gone forever. Hawking's radiation theory, which implies that black holes gradually evaporate and potentially lose all their information, directly clashes with the no information loss principle in quantum mechanics. To resolve this paradox, several ideas have emerged. One popular hypothesis is the idea of quantum entanglement. In quantum theory, particles can become entangled, meaning their states are interconnected, even when separated by vast distances. Some physicists suggest that the information consumed by a black hole could be encoded in the entanglement of particles near the event horizon. According to this idea, as the black hole radiates Hawking radiation, it gradually releases information through the subtle quantum correlations between the emitted particles and the particles trapped near the event horizon. Another solution involves the concept of firewalls. A firewall is a theoretical boundary surrounding a black hole, where the usual smooth, continuous geometry of space-time breaks down. This radical proposal suggests that instead of the familiar event horizon, there is a region of intense radiation, creating a firewall that burns any information entering the black hole. While highly controversial, the firewall hypothesis illustrates the ongoing debates about how information is handled during black hole evaporation. These differing solutions highlight the complexities and uncertainties that still surround Hawking radiation and its relationship to quantum mechanics. Even with the challenges and contradictions posed by these theories, the study of Hawking radiation continues to drive scientific inquiry into the nature of black holes and the fundamental principles of physics. As new data becomes available from astronomical observations and experiments, our understanding of these enigmatic objects may shift in unexpected ways. Whether through the discovery of primordial black holes, the observation of Hawking-like radiation in laboratory settings, or the development of new mathematical frameworks, the future of black hole research promises to be filled with exciting developments. As we turn our attention to the broader implications of Hawking radiation, it's impossible to ignore the tantalizing connection it has to the ultimate fate of the universe. The theory offers a glimpse into the future of our cosmic environment. The slow, steady evaporation of black holes will eventually lead to their disappearance. In a universe filled with countless black holes, this gradual evaporation process would unfold over a timescale so vast that it dwarfs even the longest lifespan of stars and galaxies. This far-off future raises profound questions about the ultimate end of the universe and what, if anything, could follow this final chapter. Some cosmologists speculate that the final stages of black hole evaporation might result in the production of high-energy particles or exotic forms of matter, potentially marking the end of the universe's current phase. These speculative scenarios open up exciting possibilities for understanding the ultimate fate of the cosmos. One idea is that the remnants of black holes could give birth to new universes, spawning fresh cosmic cycles in an eternal recurrence. This view touches upon the concept of a multiverse, an infinite, ever-expanding ensemble of universes, each with its own unique properties and histories. On a more philosophical note, the study of black holes and their eventual evaporation through Hawking radiation forces us to confront the limits of human knowledge. Despite decades of groundbreaking research, there are still fundamental aspects of reality that remain out of reach. Black holes, with their singularities, event horizons, and quantum complexities, embody the deep mysteries of the universe that challenge even our most advanced theories. They symbolize the limits of space-time and the edge of human understanding, reminding us that there are still questions we may never fully answer. But these unanswered questions also highlight the beauty of scientific discovery. Each breakthrough, each new insight into the behavior of black holes, brings us one step closer to understanding the true nature of the cosmos. The journey of exploring Hawking radiation is a perfect example of how the quest for knowledge is never truly finished. Just when we think we've reached the end of the line, new ideas and discoveries emerge to take us further into the unknown. The exploration of black holes and Hawking radiation represents more than just a study of celestial objects. It is an exploration of the very fabric of reality itself. As we continue to probe the nature of space, time, and matter, we gain not only answers to specific questions but also a deeper appreciation for the intricacies of the universe. Every step forward in understanding black holes takes us a little closer to answering some of the oldest and most profound questions about existence. What is the nature of space-time? How do we reconcile quantum mechanics with general relativity? What is the ultimate fate of our universe? Hawking's theory of black hole evaporation, its groundbreaking concept of Hawking radiation, has irrevocably altered our understanding of the cosmos. It has reshaped our ideas about the life cycles of black holes, the nature of entropy, and the ultimate fate of the universe. It has inspired a new generation of physicists and cosmologists to explore the farthest reaches of the universe, seeking answers to some of the most profound mysteries in science. As we continue to unravel the complex and sometimes paradoxical nature of black holes, we move ever closer to a deeper understanding of the cosmos and our place within it. As we continue to unravel the profound mysteries of black holes and Hawking radiation, it becomes clear that this theory is more than just an isolated curiosity in physics. It has profound implications for our understanding of the universe's history, its future, and its very structure. The ability of black holes to evaporate and ultimately disappear, a process predicted by Hawking's theory, challenges our deepest assumptions about the eternal nature of these cosmic objects. Black holes were once seen as the ultimate end of the line in space, regions where nothing, not even light, could escape. Yet Hawking's radiation suggests that these seemingly indestructible entities are not forever. They could eventually fade away, leaving behind nothing but radiation. The implications of this are staggering. If black holes can evaporate, what happens to the information they contain? Does it simply vanish into the ether, as Hawking initially suggested? Or does it somehow survive, encoded in the radiation emitted during their final moments? This is the black hole information paradox, one of the most profound challenges in modern physics, and one that has yet to be fully resolved. As we delve deeper into the nature of this paradox, we find that it touches on some of the most fundamental questions about the nature of reality itself. One of the reasons that Hawking radiation is so fascinating is that it links together seemingly disparate areas of physics: quantum mechanics, general relativity, and thermodynamics. Quantum mechanics deals with the behavior of subatomic particles, the smallest building blocks of nature. It tells us that particles exist in states of probability, rather than fixed positions, and that their behavior is governed by probabilities rather than certainties. General relativity, on the other hand, deals with the large-scale structure of the universe, explaining how gravity works on cosmic scales. It tells us how massive objects warp spacetime, creating the force we experience as gravity. Thermodynamics, meanwhile, governs the flow of energy and the movement of heat, and it describes the behavior of systems as they evolve towards states of higher entropy or disorder. Hawking radiation brings all these fields together. At the heart of the theory lies the concept of quantum fluctuations, tiny, unpredictable changes in the energy of a vacuum that occur even in empty space. These fluctuations give rise to virtual particles, pairs of particles that pop into existence for an instant before annihilating each other. Normally, these particles are undetectable, but near a black hole's event horizon, something extraordinary happens. One of these virtual particles can fall into the black hole, while the other escapes into space as real radiation. This radiation is what we observe as Hawking radiation. The idea that black holes can emit radiation and eventually lose mass and evaporate was a groundbreaking revelation in the field of theoretical physics. But even more remarkable is the potential that this process has to change our understanding of the cosmos. If black holes can indeed evaporate over time, then this opens up the possibility that they are not the ultimate cosmic dead ends we once thought them to be. Instead, they are transient objects that play a role in the dynamic evolution of the universe. They might not be eternal, but rather part of a cyclical process, giving rise to new phenomena as they decay. This brings us to another fascinating aspect of black hole evaporation, the timescale. The rate at which a black hole loses mass via Hawking radiation depends on its size. Larger black holes, such as those formed from the collapse of massive stars, have long lifespans, often stretching across trillions of years. Smaller black holes, on the other hand, could evaporate much more quickly. In fact, the tiniest black holes, known as primordial black holes, could have already evaporated since the beginning of the universe, given that they would have lost mass at a much faster rate. But for supermassive black holes, the process of evaporation will take so long that it is not likely to be a significant factor for the foreseeable future. This raises another question: how do we measure Hawking radiation? Since the radiation emitted by a black hole is incredibly weak and difficult to detect, especially from such immense distances, direct observation of Hawking radiation is currently beyond our technological capabilities. However, scientists are still looking for indirect evidence that would support Hawking's theory. For instance, researchers have experimented with creating analogs of black holes in laboratory settings, using condensed matter systems such as superfluids or ultra-cold atoms. These systems exhibit behaviors that mimic the properties of black holes, and some experiments have even observed phenomena that resemble Hawking radiation. While these experiments are not the same as detecting radiation from a cosmic black hole, they provide valuable insights into the fundamental principles of the theory. The study of Hawking radiation has also sparked new research into the connection between gravity and quantum mechanics. One of the greatest challenges in modern physics is reconciling the two pillars of theoretical physics: general relativity and quantum mechanics. General relativity describes the force of gravity on a large scale, such as the gravitational pull of planets and stars, while quantum mechanics explains the behavior of particles on the smallest scales. These two theories, while extraordinarily successful in their respective domains, are fundamentally incompatible. Hawking's work, especially with his radiation theory, is one of the key areas where physicists are attempting to bridge this gap. By studying how gravity behaves at the event horizon of black holes and how quantum fluctuations lead to the emission of radiation, researchers hope to uncover new insights that could lead to a unified theory of quantum gravity. This theory would be a major breakthrough in our understanding of the universe, allowing us to describe phenomena where both quantum mechanics and general relativity are important, such as the inside of a black hole or the birth of the universe itself. A unified theory could also provide answers to questions about the nature of space and time, and possibly even offer a better understanding of the origin of the universe. Yet even as we begin to peel back the layers of black hole mysteries, there are still significant unanswered questions. One of the most intriguing of these is the ultimate fate of the information that falls into a black hole. In the 1970s, Stephen Hawking proposed that when a black hole evaporates via Hawking radiation, the information contained within it is lost forever. This suggestion, known as the information loss paradox, caused an uproar in the scientific community, as it directly contradicted the fundamental principles of quantum mechanics, which state that information cannot be destroyed. The debate over whether information is truly lost in black holes continues to this day. In more recent years, some physicists have proposed alternative solutions, suggesting that the information may be preserved in some form, perhaps encoded in the Hawking radiation itself or hidden in the quantum correlations near the event horizon. Other ideas, such as the firewall hypothesis mentioned earlier, propose that information could be destroyed in extreme conditions, leading to new theories about the nature of black holes. Despite these unresolved questions, one thing is certain: Hawking radiation has profoundly altered our understanding of black holes and the cosmos. It has opened up new avenues of research, challenged old assumptions, and invited scientists to explore deeper, more fundamental questions about the universe. As our tools and techniques continue to improve, we may one day gain direct evidence for Hawking radiation and, in doing so, uncover even more astonishing revelations about the nature of space, time, and the fabric of reality itself. As we continue our exploration into the depths of Hawking radiation and black hole evaporation, it is important to reflect on the broader implications of these phenomena for our understanding of the universe. The idea that black holes might not be eternal, but instead subject to eventual decay, forces us to reconsider our concepts of time, space, and the ultimate fate of cosmic structures. While the existence of Hawking radiation remains theoretical and elusive, the potential for discovery in this field offers one of the most exciting frontiers in modern physics. One of the most fascinating aspects of Hawking's theory is the way it challenges the traditional view of black holes as being complete in their existence. For decades, scientists have seen black holes as regions of space where matter and energy disappear beyond the event horizon, never to be seen again. But with Hawking's groundbreaking proposal, this view shifts. Instead of being the cosmic finality that devours everything, black holes are now seen as transient objects that slowly dissipate over time, releasing radiation and possibly information back into the universe. This concept brings a sense of dynamism to the universe that we hadn't fully appreciated before. Furthermore, the possibility that black holes eventually evaporate suggests that they may play an essential role in the life cycle of the cosmos. Rather than being graveyards for dead stars, black holes might be involved in the creation and destruction of matter in a cyclical fashion. Imagine the profound implications for the creation of galaxies and the formation of new stars. The energy released by the evaporation of a black hole could contribute to the cosmic landscape in ways we are only beginning to comprehend. At the same time, this raises another provocative question: what happens when a black hole reaches the end of its life cycle? The idea that it could completely evaporate and leave nothing behind has significant consequences for the fundamental laws of physics. It touches on the concept of entropy, a measure of disorder or randomness in a system, and the second law of thermodynamics, which states that the total entropy of a closed system must always increase. If a black hole evaporates entirely, what becomes of the entropy it contained? Does it dissipate into the universe, or is it forever lost? These questions remain unresolved, and the search for answers could lead to groundbreaking insights into the nature of time, space, and the fundamental workings of the universe itself. One of the key motivations for studying Hawking radiation is the tantalizing potential it offers for linking quantum mechanics and general relativity. These two pillars of physics have been resistant to unification, with each theory excelling in its respective domain but struggling to reconcile with the other. General relativity describes the behavior of massive objects and the curvature of spacetime, while quantum mechanics governs the microscopic world of particles and their interactions. At the event horizon of a black hole, these two realms collide in a way that challenges our ability to describe them fully. Hawking radiation presents an opportunity to explore this intersection between quantum mechanics and gravity. The very process of radiation being emitted from the event horizon, driven by quantum fluctuations, suggests a deeper relationship between quantum theory and the behavior of black holes. If we can fully understand this radiation, it might offer the key to unlocking a theory of quantum gravity, which could bring together the principles of quantum mechanics and the laws of general relativity into a single framework. This is one of the holy grails of theoretical physics, and Hawking radiation is a central piece of the puzzle. However, even as the scientific community pushes forward with these theoretical advancements, the challenge of detecting Hawking radiation remains daunting. The radiation emitted by black holes is incredibly weak, and the most massive black holes emitted at an incredibly slow rate, making it difficult to observe directly. To detect Hawking radiation, scientists would need incredibly sensitive instruments capable of observing the faintest signals from black holes billions of light years away. At present, we do not have the technology to make such measurements. But scientists are not deterred. They are exploring indirect ways to confirm Hawking's theory, such as through experiments in laboratories and studies of cosmic phenomena. In recent years, scientists have created analogs of black holes in laboratory settings, often using systems of ultra-cold atoms or superfluids that exhibit similar behaviors to those of real black holes. In these experiments, researchers can manipulate the flow of matter and energy in ways that mimic the dynamics of black holes, allowing them to simulate Hawking radiation in a controlled environment. These laboratory experiments are not the same as observing actual cosmic black holes, but they provide important insights into how Hawking radiation might function. The hope is that these experiments will eventually provide indirect evidence of the radiation predicted by Hawking, moving us one step closer to understanding this phenomenon. But the experimental challenges are only one aspect of the puzzle. Another key issue is the black hole information paradox, the idea that, if black holes can evaporate and the information inside them is lost, it contradicts a fundamental principle of quantum mechanics. Quantum theory asserts that information is never truly lost. It is always preserved in some form, even if it is not immediately accessible. This principle has been tested time and again in quantum systems, but it seems to break down when applied to black holes. The information paradox has led to a great deal of debate among physicists, with some proposing that the information might be encoded in the Hawking radiation itself, while others suggest that it might be stored on the event horizon in some form, possibly as a holographic projection. The resolution of the information paradox is one of the greatest challenges in theoretical physics today. The debate over whether information is lost or preserved in a black hole has profound implications for our understanding of the nature of reality. If information can be lost in a black hole, it would suggest that the universe is not as deterministic as we thought, and that some events may be beyond our ability to predict or recover. On the other hand, if the information is preserved in some way, it might open up entirely new ways of thinking about the structure of space and time. The ultimate answer to this question could unlock a deeper understanding of the universe and the nature of quantum mechanics. Moreover, the very idea that black holes could evaporate over time leads to a profound re-evaluation of the ultimate fate of the universe. If black holes can slowly lose mass and eventually disappear, does that mean that the universe itself will eventually be emptied of these mysterious objects? Will the black holes that dominate the centers of galaxies vanish over time, leaving behind only the remnants of their radiation? What does this mean for the long-term future of the cosmos? As we continue to investigate the mysteries of black holes and Hawking radiation, one thing is certain: we are on the verge of a new era in our understanding of the cosmos. The discovery of Hawking radiation and the potential evaporation of black holes challenges our most fundamental assumptions about the nature of space, time, and the universe itself. It is a theory that bridges the gaps between quantum mechanics, relativity, and thermodynamics, and it offers the tantalizing possibility of a unified theory of physics. While we may not have all the answers yet, the journey to understanding these phenomena promises to be one of the most exciting and transformative adventures in the history of science. As we continue this exploration of Hawking radiation and the profound implications it has on our understanding of black holes, space, and time, it becomes increasingly clear that the story is far from over. We are only beginning to scratch the surface of the mysteries that black holes hold, and each new discovery adds layers of complexity and excitement to the narrative. Hawking's theory of black hole evaporation is not just a fascinating glimpse into the fate of these enigmatic cosmic giants, but it also raises profound questions that touch on the very nature of the universe itself. One of the most intriguing aspects of Hawking's theory is how it might force us to rethink the concept of time. In classical physics, time is seen as a continuous and unidirectional flow, one that is tied to the progression of events and the unfolding of the universe. The discovery that black holes can evaporate and release radiation over time challenges this linear view. If black holes, which were once considered eternal, can eventually dissipate, what does this mean for the concept of time itself? Could the universe itself one day reach a state where all black holes have evaporated, leaving behind a cosmic void? This leads to another question: what happens after the black hole has completely evaporated? In theory, once a black hole has emitted all of its Hawking radiation, it would eventually reach a state where there is no more mass or energy remaining. The final stage of black hole evaporation is thought to result in the disappearance of the black hole entirely, leaving behind no trace of its existence. This ultimate fate is a deeply unsettling thought for many physicists, as it suggests that even the most massive and powerful objects in the universe could one day cease to exist, fading into nothingness. The idea of a black hole disappearing completely is tied to the concept of entropy. In thermodynamics, entropy refers to the measure of disorder or randomness in a system. According to the second law of thermodynamics, the entropy of a closed system must always increase over time. As a black hole evaporates, it releases Hawking radiation, which is thought to carry away the black hole's entropy. However, if the black hole eventually disappears, what happens to this entropy? Does it simply dissipate into the universe, or is it somehow preserved in the radiation emitted by the black hole? The resolution to this question could have far-reaching implications for our understanding of entropy, the nature of information, and the ultimate fate of the universe. Furthermore, the possibility that black holes evaporate and eventually disappear forces us to reconsider the role of black holes in the larger cosmological picture. Historically, black holes have been viewed as graveyards for matter, where stars, planets, and even light are swallowed up beyond the event horizon. However, the idea that black holes can dissipate over time introduces a dynamic element to their nature. Rather than being static and eternal, black holes are now seen as objects that are born, evolve, and eventually die, just like any other celestial body. This dynamic view of black holes opens up new possibilities for understanding the evolution of galaxies and the broader structure of the universe. For instance, many galaxies, including our own Milky Way, harbor supermassive black holes at their centers. These black holes are thought to play a crucial role in the formation and evolution of galaxies, influencing the movement of stars and the distribution of matter within the galaxy. If these supermassive black holes can eventually evaporate, what does this mean for the future of galaxies? Will their centers, once dominated by black holes, transform into something entirely different? In a broader context, the evaporation of black holes could have profound implications for our understanding of the long-term future of the universe. If black holes can gradually lose mass and energy over time, could this process eventually lead to a heat death of the universe, where all matter has been dispersed and the universe has reached a state of maximum entropy? This scenario, known as the Big Freeze, is one of the most widely discussed outcomes for the far future of the cosmos. The idea that black holes could contribute to this process by gradually evaporating adds a new layer of complexity to the story of the universe's ultimate fate. Despite the challenges of directly observing Hawking radiation or detecting the evaporation of black holes, there is a growing body of indirect evidence that supports the theory. In particular, studies of the cosmic microwave background radiation and the behavior of supermassive black holes in distant galaxies provide tantalizing clues that may one day lead to a breakthrough in our understanding of black hole evaporation. Scientists are also exploring other theoretical models, such as the concept of black hole firewalls, which suggests that the event horizon of a black hole could be a turbulent region where extreme quantum effects take place. These models are still speculative, but they offer new avenues for research that could shed light on the mysteries of black holes and their eventual demise. As we look ahead to the future of black hole research, the potential for new discoveries is boundless. Advances in observational technology, such as the upcoming James Webb Space Telescope and next-generation radio telescopes, will allow us to study black holes in greater detail than ever before. In particular, these instruments may allow us to observe the behavior of matter and radiation around black holes in real time, providing new insights into the process of Hawking radiation and the eventual evaporation of black holes. At the same time, the theoretical work being done in the fields of quantum mechanics and general relativity holds the promise of groundbreaking revelations. As scientists continue to probe the nature of black holes and the role of quantum fluctuations in their behavior, we may one day uncover new principles of physics that redefine our understanding of space, time, and the universe itself. The potential for a unified theory of quantum gravity, which would seamlessly integrate the principles of quantum mechanics with the laws of general relativity, is a tantalizing goal for many physicists. Hawking radiation, as a key element in the search for this theory, could provide the missing link that bridges the gap between these two seemingly incompatible realms of physics. Moreover, the search for Hawking radiation and the study of black hole evaporation could have practical implications for technology and engineering. While this might sound far-fetched, the deep understanding of quantum processes that emerges from this research could lead to innovations in fields such as quantum computing, materials science, and even space exploration. The principles of quantum mechanics, once fully understood, have the potential to revolutionize the way we interact with the world around us. The study of Hawking radiation and the evaporation of black holes is one of the most exciting and thought-provoking areas of modern physics. It challenges our understanding of the cosmos, forces us to confront deep questions about time, space, and entropy, and offers the tantalizing possibility of uncovering a unified theory of physics. While there is still much to learn and discover, the potential for breakthroughs in this field is immense. As we continue to explore the mysteries of black holes, Hawking radiation, and the ultimate fate of the universe, we are embarking on a journey that promises to redefine our understanding of reality itself. As we continue our journey through the complex landscape of black holes and the implications of Hawking radiation, it's essential to delve even deeper into the nature of the radiation itself and how it challenges some of the most fundamental principles of physics. To fully grasp the implications of black hole evaporation, we need to examine what happens at the quantum level and how this ties into our broader understanding of the universe. Hawking's breakthrough was revolutionary because it combined two concepts that were previously seen as separate: the quantum world and the large-scale world of general relativity. In classical physics, the universe was understood through the lens of Einstein's theory of general relativity, where space and time were interconnected in a continuous fabric known as spacetime. In contrast, quantum mechanics dealt with the tiny, discrete particles that make up matter and energy, operating under different rules than those governing the cosmos on large scales. What Hawking did was show that these two realms are connected in ways that are still being explored. At the heart of Hawking radiation is a quantum phenomenon called vacuum fluctuations. The idea here is that, in the vacuum of space, there are no empty regions. Instead, even in a perfect vacuum, virtual particles and antiparticles spontaneously appear and annihilate each other at incredibly small scales. These particles exist for brief moments and then disappear, leaving no trace. However, near the event horizon of a black hole, something extraordinary happens. The intense gravitational field near the event horizon can separate these particle-antiparticle pairs before they have a chance to annihilate each other. One of the particles might fall into the black hole, while the other escapes into space, becoming what we observe as Hawking radiation. This process of particle creation at the event horizon is a key part of how black holes evaporate over time. The escaping particles carry away energy from the black hole, and this energy loss causes the black hole to lose mass. Over vast periods, this loss of mass could lead to the eventual disappearance of the black hole, as it slowly but surely radiates away all of its energy. But here's where things get even more interesting. The nature of the radiation emitted by black holes is tied to the quantum properties of the particles involved. Unlike the radiation emitted by everyday objects, which typically follows a predictable pattern of energy emission, Hawking radiation is unpredictable and random. The energy of the emitted radiation can vary, and this randomness is rooted in the uncertainty principle of quantum mechanics. This principle suggests that we cannot precisely know both the position and momentum of a particle at the same time, introducing an inherent unpredictability in the behavior of particles near the black hole's event horizon. This randomness ties into a broader puzzle that scientists are still grappling with: the information paradox. According to the laws of quantum mechanics, information about a particle's state cannot be lost. This is known as the principle of unitarity. However, when a particle falls into a black hole, it seems to disappear beyond the event horizon, and the information about that particle is thought to be lost forever. Hawking radiation, by allowing particles to escape the black hole, seems to contradict this idea, as it suggests that information might be leaking out in the form of radiation. The question arises: is the information truly lost, or is it encoded in the radiation in a way we don't yet understand? This paradox remains one of the most exciting and perplexing challenges in modern physics. The resolution of the information paradox could provide a key insight into the nature of quantum gravity, which is the search for a theory that successfully combines general relativity and quantum mechanics. This unified theory is one of the holy grails of physics, as it would allow us to describe the behavior of the universe on all scales, from the tiniest subatomic particles to the vastest galaxies and black holes. Understanding how information is preserved or lost in the process of black hole evaporation could hold the key to unlocking this unified theory. Beyond theoretical implications, the discovery of Hawking radiation also opens the door to a new way of thinking about the fate of the universe itself. The idea that black holes can eventually evaporate and disappear challenges the long-standing assumption that black holes are permanent fixtures in the cosmos. In a way, black holes represent an end point for matter and energy, a place where everything is drawn into a singularity and lost. But Hawking's theory suggests that this is not the case. Even black holes, with their immense gravitational pull, are not immune to the passage of time. The fact that they can slowly lose mass and energy over billions of years introduces a new dimension to the concept of cosmic evolution. This has profound implications for our understanding of the long-term future of the universe. As black holes gradually evaporate, they will leave behind a much emptier universe. Stars will burn out, galaxies will drift apart, and the remnants of black holes will slowly disappear, leaving behind a cold, dark, and mostly empty expanse. This vision of the far future is one of the most sobering prospects in cosmology, a universe that gradually succumbs to entropy and fades into nothingness. At the same time, the process of black hole evaporation also raises interesting questions about the possibility of recycling matter and energy. As black holes evaporate, they release a tremendous amount of energy in the form of Hawking radiation. Could this energy be harnessed in some way? Could we find a way to tap into the radiation emitted by black holes to generate power or fuel? While this might sound like science fiction, it's not entirely outside the realm of possibility. The laws of quantum mechanics are still full of surprises, and who knows what discoveries future generations of scientists will make about the nature of energy, space, and time. As technology advances and our understanding of quantum mechanics deepens, we may one day be able to detect Hawking radiation directly. Currently, this remains an elusive goal, as the radiation emitted by black holes is incredibly faint and difficult to observe. However, scientists are making strides in developing new techniques for detecting these subtle quantum effects, and the search for direct evidence of Hawking radiation is one of the most exciting areas of research in modern physics. If we succeed in detecting Hawking radiation, it would not only confirm Hawking's groundbreaking theory but also open up new avenues for exploring the mysteries of black holes and the quantum nature of the universe. The possibility of detecting Hawking radiation also raises another intriguing question. If black holes can eventually evaporate and disappear, does this mean that the end of a black hole is not truly the end? Could the energy and information contained within a black hole be released back into the universe in some way, perhaps leading to the formation of new cosmic structures or phenomena? The answers to these questions may be hidden in the complexities of quantum gravity and the still unknown behavior of matter and energy near black hole event horizons. As we look to the future, the implications of Hawking's theory will continue to shape our understanding of black holes, space, and the very fabric of reality itself. While there is still much to learn and discover, the theory of Hawking radiation has already had a profound impact on the way we think about the universe. It challenges us to rethink the nature of black holes, the fate of matter, and the ultimate fate of the cosmos. And as we continue to probe the mysteries of the quantum realm and the vast expanses of space, we can be sure that the legacy of Stephen Hawking's work will continue to inspire and guide generations of scientists, thinkers, and dreamers. As we delve deeper into the fabric of the universe, the concepts of black hole evaporation and Hawking radiation raise further profound questions about the fate of matter, energy, and information. For decades, we have thought of black holes as cosmic traps, regions where nothing, not even light, can escape. But Stephen Hawking's theory challenges this view by introducing the idea that black holes are not permanent, that they can slowly lose mass over time and ultimately vanish, changing our understanding of these mysterious objects. To fully appreciate the significance of Hawking radiation, it's important to revisit the nature of black holes themselves. A black hole forms when a massive star collapses under its own gravity, compressing its matter into an infinitely dense point known as a singularity. Around this singularity lies the event horizon, a boundary beyond which nothing can escape, not even light. The event horizon is what gives black holes their black nature, as anything crossing this threshold is drawn inexorably inward, lost to the rest of the universe. In classical general relativity, once matter crosses the event horizon, it is thought to be forever trapped. But quantum mechanics, particularly the theory of quantum field theory, introduces new possibilities. According to quantum field theory, even in a perfect vacuum, space is never truly empty. Instead, pairs of virtual particles constantly pop in and out of existence. These particles are not directly observable, as they annihilate each other almost instantaneously. However, near the event horizon of a black hole, these particles can become separated before they have a chance to annihilate, leading to the creation of Hawking radiation. This brings us to a crucial point. The nature of the radiation emitted by black holes is not a passive event but an active process that alters the very nature of the black hole. The emission of Hawking radiation means that a black hole is, in effect, radiating away its mass over time. This process occurs because, as one member of a particle-antiparticle pair falls into the black hole, the other escapes into space, carrying away energy. As a result, the black hole loses mass with each emission of radiation. One of the key insights from Hawking's theory is that the mass of the black hole decreases with time as a result of this radiation. The more massive the black hole, the slower the rate of evaporation, but over incredibly long timescales, even the most massive black holes will eventually lose enough mass to disappear. For a stellar mass black hole, this process would take longer than the current age of the universe, but for smaller black holes, the evaporation could occur more quickly. As black holes lose mass and energy, their size decreases. This effect has important consequences for the eventual end state of the black hole. As the black hole shrinks, its gravitational pull becomes weaker, and the intensity of Hawking radiation increases. The smaller the black hole, the faster it radiates away its energy, creating a sort of feedback loop. This final phase of evaporation, where the black hole rapidly shrinks and the intensity of the radiation skyrockets, is known as the final explosion, or black hole death. However, the fate of the black hole before its ultimate demise is still uncertain. We are left with several unanswered questions. What happens to the information that falls into the black hole? Does it truly get lost, as some have suggested, or is it encoded in the Hawking radiation? Does the black hole's evaporation process preserve the laws of quantum mechanics, or does it reveal a deeper flaw in our understanding of how the universe works at the most fundamental level? The resolution of the black hole information paradox is one of the most exciting and contentious areas of research in theoretical physics. Some scientists argue that the information is lost to the black hole's singularity, forever trapped within its depths. Others suggest that the information could be encoded in the Hawking radiation itself, albeit in a highly scrambled form. One popular theory, known as the firewall hypothesis, suggests that as a black hole evaporates, a wall of high-energy radiation could form near the event horizon, destroying any information that falls in. In recent years, the development of new ideas, such as the holographic principle and the concept of quantum gravity, has led to new approaches to understanding the fate of information in black holes. The holographic principle, for example, suggests that all of the information contained within a volume of space can be described by the information on the boundary of that space, which could have implications for how information is encoded and preserved in the context of black holes. Despite these efforts, a complete resolution of the information paradox remains elusive. Yet, the work done by Hawking and other physicists in exploring these ideas has sparked a revolution in our thinking about black holes, quantum mechanics, and the very nature of space and time. The implications of Hawking radiation are not limited to theoretical physics. They extend to our broader understanding of the cosmos and the ultimate fate of the universe itself. If black holes can evaporate, what does this mean for the long-term future of the universe? Will all black holes eventually vanish, leaving behind a dark and empty universe? Or is it possible that the energy released by evaporating black holes could lead to new forms of cosmic evolution? The answers to these questions are still unknown, but they offer a tantalizing glimpse into the future of the universe. As we continue to explore the mysteries of black holes, it's also worth considering the technological implications of Hawking radiation. While we are currently unable to observe this radiation directly due to its faintness, the discovery of ways to detect it could have far-reaching implications for the future of physics. If we could directly observe Hawking radiation, we would not only confirm Hawking's groundbreaking theory but also open new doors for understanding quantum mechanics, the nature of space-time, and the behavior of matter and energy in extreme environments. Furthermore, the study of black hole evaporation could lead to practical applications in areas such as energy generation. The process of Hawking radiation involves the emission of high-energy particles, and understanding this phenomenon could eventually lead to the development of new technologies that harness these particles. This might sound far-fetched, but the history of science is full of surprising breakthroughs that once seemed impossible. Just as we have harnessed the power of atoms for energy and communication, we may one day discover ways to harness the energy released by black holes as they evaporate. We are reminded of the incredible depth of human curiosity and our unyielding desire to understand the universe. Hawking's theory has not only reshaped our understanding of black holes but also challenged our most basic assumptions about the nature of space, time, and reality itself. The questions raised by his work are as profound as they are complex, and the journey to answer them is far from over. The legacy of Hawking radiation will continue to shape the future of physics and cosmology, guiding future generations of scientists, thinkers, and dreamers as they seek to unravel the mysteries of the universe. Whether through direct observations of Hawking radiation, the resolution of the information paradox, or the discovery of new theories of quantum gravity, we are certain to witness even more groundbreaking discoveries in the years to come. The universe is vast, mysterious, and full of wonder, and as long as we continue to ask questions, we will keep pushing the boundaries of what we know and what we can imagine. As we continue to explore the deeper implications of Hawking radiation, it's essential to grasp the broader framework in which this theory fits. Stephen Hawking's work doesn't just touch on the mysterious nature of black holes but on the very fabric of space-time itself. The way in which he connected quantum mechanics with general relativity, two theories that were previously considered incompatible, forever changed the landscape of theoretical physics. In essence, Hawking radiation is not just a phenomenon related to the life cycle of black holes, but a manifestation of how quantum physics operates in extreme conditions that we may one day be able to test with advanced technology. We've already established that Hawking radiation is based on the principle of quantum mechanics, which tells us that even in seemingly empty space, particles are constantly popping in and out of existence. These virtual particles, as they're called, are part of the quantum vacuum fluctuations, a concept that has taken physicists years to fully comprehend. The big breakthrough came when Hawking realized that near a black hole's event horizon, these virtual particles could be separated by the immense gravitational forces at play. Now, let's take a moment to reflect on how extraordinary this concept is. We're talking about a force strong enough to stretch the very fabric of spacetime, pulling virtual particles apart in a way that causes one of them to be sucked into the black hole, while the other escapes into space. The escaping particle carries away energy in the form of radiation, which we refer to as Hawking radiation. This radiation leads to a slow loss of mass from the black hole, eventually causing it to shrink and, in the distant future, disappear entirely. However, even as we appreciate the elegance of this theory, we must also acknowledge the challenges it presents to our understanding of the universe. For example, how does this radiation interact with the fabric of space-time? If black holes can lose mass through this process, does it mean that the laws of thermodynamics need to be re-evaluated in light of this new phenomenon? What happens to the entropy, essentially, the amount of disorder, associated with a black hole as it evaporates? These are fundamental questions that physicists are still grappling with today. One of the reasons the theory is so mind-boggling is that it essentially proposes that black holes, once thought to be permanent cosmic structures, have a lifespan, albeit one that can span trillions of years. In fact, the time it would take for a black hole to evaporate completely due to Hawking radiation is proportional to its mass. Smaller black holes, such as those with just a few times the mass of our Sun, would evaporate relatively quickly, on the order of a few billion years. Larger black holes, like supermassive black holes, would take far longer, but even they would eventually fade away. This concept of a death for black holes is something that had never been considered in traditional models before Hawking's groundbreaking work. The issue of time and scale is essential when considering the long-term implications of Hawking radiation. While we can only speculate about how a black hole might evaporate over such vast timescales, it also opens up questions about the future of the universe. We are accustomed to thinking of the universe as a place filled with immutable objects, stars, planets, galaxies, and yes, black holes. However, The process of black hole evaporation, combined with the expansion of the universe, means that our cosmos may eventually reach a state where all that remains are diffuse particles and radiation. This leads us into a realm of even bigger questions. If Hawking radiation can cause black holes to evaporate, what happens to the information that they've consumed? We've already touched on the infamous black hole information paradox, which remains one of the most hotly debated topics in modern theoretical physics. In simple terms, this paradox arises because according to quantum mechanics, information cannot be destroyed. But when matter and energy fall into a black hole, it seems to be lost forever, as nothing can escape once it crosses the event horizon. Hawking's theory initially suggested that this information might be lost, but this sparked intense debates, leading to various hypotheses and possible resolutions. One of the most promising avenues of research in this regard involves the idea of quantum entanglement, and the possibility that information may be encoded in the Hawking radiation itself. Some physicists believe that the radiation escaping from a black hole could carry information about the objects that fell into it, but this information would be incredibly scrambled and difficult, if not impossible, to decode. This idea led to the holographic principle, a theory which posits that all of the information contained within a black hole might be represented by information on the surface of the event horizon, a two-dimensional hologram that encodes the three-dimensional structure of the black hole. Though we're still far from fully understanding how this works, the implications of the holographic principle are profound. It suggests that the universe itself might be like a hologram, where the information about the three-dimensional world we experience is encoded on a two-dimensional surface. If this idea holds, it could bridge the gap between quantum mechanics and general relativity, the two pillars of modern physics that have yet to be unified in a single theory. In the decades since Hawking's discovery, there have been many efforts to test and refine his predictions. Despite the mathematical elegance of his theory, directly observing Hawking radiation remains an immense challenge. The radiation is incredibly weak and faint, making it nearly impossible to detect with current technology. Furthermore, since the radiation is emitted by objects that are often many millions or billions of light years away, it's a long shot that we will be able to directly observe it in the near future. However, scientists are not deterred. Researchers are exploring new and innovative ways to detect Hawking radiation indirectly. For example, scientists are looking at analog black holes, which are not true black holes, but systems that mimic certain aspects of black holes in laboratory settings. By studying these analogs, researchers hope to gain insights into how Hawking radiation might manifest in real black holes, and eventually, develop methods for detecting it in the cosmos. Moreover, advancements in technology and telescopes, particularly in the fields of high-energy astrophysics and gravitational wave astronomy, offer new hope for observing the effects of Hawking radiation. Even if we can't detect the radiation itself, the presence of black holes and the way they interact with their environment might provide us with indirect evidence. The search for Hawking radiation is not just an academic exercise, it holds the potential for profound discoveries about the universe and the fundamental laws that govern it. As we continue to investigate the nature of black holes and their eventual evaporation, we must also think about the philosophical implications. If black holes can evaporate and ultimately vanish, does this suggest that all things in the universe are transient, even the most seemingly permanent objects? Are black holes simply a phase in the life cycle of matter and energy, much like stars that are born, live, and die? And what does this mean for the ultimate fate of the universe itself? If black holes can evaporate and energy can be released through Hawking radiation, could this process lead to new forms of cosmic evolution? While these questions may seem speculative, they are an essential part of the journey toward understanding the universe in its entirety. Just as we once thought the Earth was the center of the universe, and just as we once believed black holes were immortal, the study of Hawking radiation forces us to confront the possibility that everything, no matter how grand or mysterious, has an end, and that end might be more complex and surprising than we ever imagined. As we push forward in unraveling the mysteries of Hawking radiation, it's critical to dive deeper into how this theory challenges the way we think about space, time, and the universe itself. We've discussed the evaporation of black holes, but the implications of this process stretch far beyond just these enigmatic objects. The potential for Hawking radiation to unlock hidden truths about the fabric of the universe itself is one of the most profound aspects of Stephen Hawking's work. Not only does it force us to confront the idea that black holes may not be as eternal as once thought, but it also hints at a deeper, more interconnected structure of reality. One of the most fascinating things about Hawking radiation is how it potentially reshapes our understanding of energy conservation and entropy. In classical physics, energy conservation is a fundamental principle. Energy can neither be created nor destroyed, only transformed. However, in the case of Hawking radiation, we encounter a situation where black holes slowly lose mass over time as they emit this radiation. This presents an apparent paradox. How can a system, which is supposed to conserve energy, slowly shed its mass without violating the laws of physics? Here lies the connection to the concept of entropy, a measure of disorder in a system. In classical thermodynamics, the second law states that entropy tends to increase over time in an isolated system. With the process of Hawking radiation, as a black hole loses mass and shrinks, one might expect the entropy of the system to decrease. But if information is truly encoded in the radiation, something that is still debated by physicists, then the process might not violate the second law. Instead, the information could be preserved in some way, preventing the collapse of entropy into complete disorder. The idea that black holes could evaporate without violating these fundamental laws is truly remarkable. It suggests that our understanding of thermodynamics, quantum mechanics, and general relativity might need a radical overhaul. This is not just about one small corner of physics. It is about understanding the very laws that govern how the universe works. Black holes, which were once thought of as the ultimate cosmic prisons, places where nothing could escape, not even light, are now seen as dynamic, ever-changing entities that are subject to the same physical principles that govern everything else in the universe. Another critical implication of Hawking's theory is the challenge it poses to our understanding of the singularity at the center of a black hole. According to general relativity, the singularity is a point where gravitational forces become infinitely strong, and space-time curves to such an extent that the laws of physics, as we know them, break down. In this region, time itself is believed to stop. This is where matter is compressed to an infinite density, making it impossible to describe using the tools of modern physics. However, Hawking radiation introduces a potential solution to this issue. While general relativity predicts that the singularity is a place where all physical laws collapse, the quantum mechanical approach of Hawking radiation suggests that the radiation emanating from the event horizon might carry clues that could one day allow us to reconcile the singularity with quantum mechanics. If the information contained within a black hole can escape in the form of radiation, it could help shed light on what happens at the center of a black hole, even if we cannot directly observe it. The resolution of this conflict between general relativity and quantum mechanics is one of the most exciting and perplexing challenges in modern theoretical physics. It could hold the key to understanding how the universe operates at its most fundamental level. Some physicists hope that the study of Hawking radiation and the behavior of black holes will eventually lead to the discovery of a theory of everything, a unified framework that combines the two pillars of physics, general relativity and quantum mechanics, into one cohesive theory. This could answer some of the biggest questions in science, such as the nature of space and time, the origin of the universe, and the ultimate fate of all matter and energy. For now, however, we are left to explore these concepts through mathematical models and indirect observations, as the direct detection of Hawking radiation remains beyond our technological reach. In the future, it's possible that more powerful telescopes and advanced detectors will allow us to measure the faint traces of this radiation, potentially giving us the first concrete evidence of its existence. Until then, the hunt for Hawking radiation continues to inspire researchers to think about the universe in entirely new ways, as they strive to connect the dots between theoretical physics, experimental data, and the mysteries of the cosmos. As we consider the broader impact of Hawking radiation on our understanding of the universe, we must also take a moment to appreciate the historical significance of this theory. Stephen Hawking's groundbreaking work on black holes and radiation did not come in a vacuum. It was the culmination of centuries of scientific inquiry and discovery. From Isaac Newton's laws of motion and gravity to Albert Einstein's theory of general relativity, the journey to understanding the most extreme phenomena in the universe has been a long and winding one. And yet, Hawking's work, which bridged the gap between quantum mechanics and general relativity, represents one of the most revolutionary advances in the history of science. What Hawking did was not just to provide a mathematical framework for understanding the radiation emitted by black holes. He also posed a deeper philosophical question about the nature of the universe itself. By suggesting that black holes can lose mass and eventually evaporate, he forced us to reconsider the idea of cosmic permanence. In a universe governed by the laws of physics, nothing, either stars, planets, nor even black holes, is truly eternal. Everything is subject to change, decay, and transformation. This realization has profound implications, not just for our understanding of black holes, but for how we think about the universe on the largest and smallest scales. It's a reminder that even the most mysterious objects in the cosmos, which once seemed to defy our understanding, are ultimately governed by the same laws of physics that govern the world around us. Just as a star can be born, live, and die, so too can a black hole. And in the future, as our technology improves, we may gain more insight into the process of black hole evaporation, ultimately revealing new aspects of the universe that are hidden from our view today. The more we explore Hawking radiation and the implications of black hole evaporation, the more we find that this is just the tip of the iceberg. The universe is a vast and complex place, filled with mysteries waiting to be uncovered. Every breakthrough, every new discovery, opens up new questions and new paths for exploration. As scientists continue to study Hawking radiation and its effects, we are reminded that our understanding of the cosmos is always evolving. And perhaps, in the distant future, we will look back at Hawking's work as the foundation upon which we built a much deeper and more complete understanding of the universe. For now, we continue to wonder about the fate of black holes, their evaporation, and the role that Hawking radiation plays in shaping the ultimate destiny of the universe. While we may not have all the answers yet, the journey to understanding these cosmic phenomena is one that will continue to captivate and inspire generations of scientists, philosophers, and curious minds alike. As we continue exploring the mysteries of black holes and Hawking radiation, we dive into an even deeper web of questions and possibilities. Hawking's theory, groundbreaking as it was, did not just present a physical phenomenon, it posed a philosophical challenge to how we understand reality itself. What does it mean for the very fabric of space-time if black holes can evaporate? If they are not permanent structures, what happens to the information contained within them? One of the most controversial aspects of Hawking's theory involves the so-called information paradox. According to quantum mechanics, information about the physical state of a system should always be preserved. This is known as the principle of unitarity. Yet, if black holes evaporate via Hawking radiation and eventually disappear, the information contained within them should also vanish. This seemingly violates the fundamental tenet of quantum theory, creating a paradox that has perplexed physicists for decades. Hawking himself famously debated this issue for many years, and his stance evolved over time. Initially, he believed that the information was indeed lost, a position that was controversial and led to intense debates in the physics community. However, in more recent years, Hawking began to reconsider this stance, suggesting that the information might not be lost after all. This shift in perspective opened the door to new ideas and potential resolutions of the paradox. Some theories propose that the information could be encoded in the Hawking radiation itself, while others speculate that black holes could be holographic, meaning that their information is stored on the event horizon in a way that is not immediately obvious to us. To understand the information paradox more clearly, let's step back and consider what happens when an object crosses the event horizon of a black hole. Once inside, nothing, not light, not matter, can escape. But this doesn't mean that the object ceases to exist or that its information disappears. In the world of quantum mechanics, even seemingly lost, information may still have an effect, lingering in ways that are not immediately apparent. Some have likened this situation to the holographic principle. a concept in theoretical physics that suggests that all of the information about a volume of space can be encoded on the surface that bounds that volume, such as the event horizon of a black hole. One theory that has emerged to resolve the information paradox is the idea of black hole complementarity. According to this idea, the information about what falls into a black hole is not lost but rather encoded in the radiation that escapes from the black hole. To an outside observer, it seems as though the information is lost as the black hole evaporates. However, to an observer falling into the black hole, the information might still exist in some form inside. Essentially, different observers may have different perspectives on what happens to the information, but no observer will ever see it disappear completely. In the decades following Hawking's initial publication of his theory of black hole evaporation, these ideas have become central to some of the most exciting research in theoretical physics. A major aspect of this research involves string theory and its potential to reconcile the worlds of quantum mechanics and general relativity. String theory offers a framework in which the forces of the universe, gravity, electromagnetism, and the strong and weak nuclear forces, are all manifestations of one fundamental entity, tiny, vibrating strings. This theory has the potential to explain many of the paradoxes surrounding black holes, including the issue of information loss. A significant breakthrough in string theory and black hole physics came with the development of the AD/CFT correspondence, a concept in theoretical physics that posits a relationship between two types of theories, those describing the interior of a black hole, the AD side, and those describing the surface of a black hole, the CFT side. This correspondence has provided new insights into how information might be preserved in black holes, offering a way to study the information paradox and potentially resolve it. The idea is that the information about everything inside a black hole might be encoded in the radiation that leaks from the event horizon, just as a hologram encodes a three-dimensional image in a two-dimensional surface. The implications of these ideas are profound. If the information paradox can be resolved, it would represent a major breakthrough in our understanding of quantum mechanics, general relativity, and the fundamental structure of the universe. It would also change the way we think about the nature of space, time, and gravity. Could black holes be the key to unlocking a new understanding of the universe, one that unites all of physics into a coherent whole? The more we learn about black holes and Hawking radiation, the closer we come to answering that question. In addition to the information paradox, Hawking's theory has led to another fascinating line of inquiry, the potential role of black holes in the ultimate fate of the universe. The idea that black holes can eventually evaporate raises a crucial question: what happens when they disappear? If a black hole evaporates completely, will it leave behind a vacuum, a void where matter and energy once were? Or will the process of evaporation lead to some new state of matter or energy? Some physicists speculate that black holes may play a significant role in the ultimate destiny of the universe. As black holes evaporate, they might release vast amounts of energy, potentially triggering new processes or transformations in the cosmos. For instance, the Hawking radiation emitted by black holes could lead to the formation of new particles or the creation of new structures in space. This idea ties into broader theories of the universe's end, such as the concept of the Big Freeze, or the heat death of the universe, where all stars burn out and black holes eventually evaporate, leaving a dark and empty cosmos. On the flip side, others speculate that black holes might be part of a cyclical process, where they eventually collapse into new structures or give rise to new universes. This idea aligns with the theory of the multiverse, which proposes that our universe might be just one of many in a vast cosmic landscape, each with its own set of physical laws. In this scenario, black holes could be portals or gateways between different universes, suggesting that the process of black hole evaporation is not the end of the story but rather a transition to something entirely new. As we continue to study Hawking radiation and black holes, we are confronted with the mind-bending reality that the universe is far stranger and more complex than we ever imagined. Every new discovery, every new theory, seems to open up a new layer of mysteries, challenging us to rethink everything we know about the cosmos. The more we learn about black holes and their role in the universe, the more we realize how much is still unknown, and how much potential there is for future breakthroughs. Hawking's legacy is not just in the equations he wrote or the theories he proposed. It lies in the way he inspired a new generation of scientists to question the nature of reality itself. His work on black holes and Hawking radiation has opened up new avenues of research and exploration that may one day revolutionize our understanding of the universe. And as we continue to probe the deepest reaches of space, we are reminded that the greatest mysteries are often the ones that challenge our very understanding of time, space, and existence itself. As we look to the future, the study of black holes, Hawking radiation, and the fundamental questions they raise will continue to shape the course of physics for generations to come. The search for answers is far from over, and with each passing day, we inch closer to uncovering the secrets of the universe's most enigmatic objects. From the possibility of new insights into quantum gravity to the potential for discovering new realms of reality, the journey to understand black holes and their radiation is one that will captivate and inspire future scientists, thinkers, and explorers. Stephen Hawking's work is a reminder that the universe is full of mysteries, and the answers we seek may be more extraordinary than we ever imagined. Whether it's the evaporation of black holes, the nature of time and space, or the ultimate fate of the universe, the questions that Hawking raised will continue to resonate throughout the scientific community for years to come. The more we explore, the more we realize just how little we truly know, and how much more there is to discover. As we venture further into the intricacies of black holes and Hawking radiation, it's important to highlight the profound impact this theory has had not only on theoretical physics, but also on our broader understanding of the universe. While Stephen Hawking's work has dominated the conversation, it has sparked a wave of debates, discoveries, and alternative theories, each adding layers to our comprehension of black holes and their true nature. One of the more fascinating areas of exploration that has emerged from the study of black holes is the connection between quantum mechanics and general relativity. These two pillars of modern physics have long been seen as incompatible. Quantum mechanics, the theory that describes the behavior of the very small, operates on principles that seem to defy our classical understanding of space and time. General relativity, on the other hand, deals with the behavior of massive objects and the curvature of space-time, providing an accurate description of large-scale phenomena like the motion of planets and the dynamics of black holes. Hawking's work, particularly the concept of Hawking radiation, has become a central piece of the puzzle in the search for a theory of quantum gravity, one that unites these two seemingly contradictory realms. The quest for a unified theory has driven many physicists to explore new and exciting frameworks. One such framework is string theory, which posits that the fundamental particles of nature are not point-like objects but instead tiny, vibrating strings. These strings could, in principle, explain both the quantum mechanical and gravitational aspects of the universe. In this theory, black holes are not simply compact masses of matter. They are multidimensional objects with a rich internal structure that can be understood using the principles of quantum mechanics. String theory suggests that black holes might have an underlying, quantum, structure, where particles and fields are woven together in complex patterns. This insight has led to the idea that the information lost in a black hole might not be lost after all. Instead, it could be encoded in the microscopic vibrations of these quantum strings, waiting to be revealed through further advancements in theoretical physics. This concept is known as the holographic principle, and it suggests that the three-dimensional world we experience may be a projection of information encoded on a two-dimensional surface, like the event horizon of a black hole. The holographic principle is a striking idea, implying that everything in the universe, from the stars in the sky to the very fabric of space-time, might be a hologram. This idea has been used to propose that the information falling into a black hole is stored on the event horizon, with the internal structure of the black hole serving as a sort of quantum archive. If this is the case, then Hawking radiation may not be a simple random process of particles popping in and out of existence, but rather a carefully orchestrated interaction between quantum fields at the black hole's edge. Another important development that has come out of the study of Hawking radiation is the potential link between black holes and the concept of the multiverse. The multiverse theory suggests that our universe is just one of many that exist simultaneously, each with its own set of physical laws. If black holes serve as windows to other universes, as some theorists suggest, then Hawking radiation might be the means by which information about our universe is transmitted to other parts of the multiverse. This raises the tantalizing possibility that black holes could be conduits, linking not just different regions of space and time, but entire universes, each with its own unique properties and fundamental constants. This idea leads to the question of what lies beyond the event horizon of a black hole. As we know, anything that crosses the event horizon is seemingly lost to the outside world. But what if this boundary is not the final word on the fate of matter and energy? What if black holes are not just destructive, but transformative, serving as gateways to other realms of existence? Such speculations push the boundaries of what we know about physics and challenge our assumptions about the nature of reality itself. But let's return to the core issue at hand, the evaporation of black holes and the mystery of their ultimate fate. According to Hawking's original theory, the process of Hawking radiation leads to the gradual evaporation of black holes over incredibly long periods of time. This process is extremely slow for large black holes, which can take billions of years to evaporate completely. However, for small black holes, the process would be much faster. In fact, it is theorized that microscopic black holes, if they exist, could evaporate almost instantaneously, releasing vast amounts of energy in the process. This raises an important question: if a black hole evaporates completely, what remains? The traditional view of black holes is that they represent a sort of cosmic sinkhole, swallowing everything in their path and leaving nothing behind. But Hawking's theory suggests that black holes do not have to be permanent. They can slowly lose mass and energy through Hawking radiation, eventually disappearing altogether. When they do, is there any trace of their existence left? Or is the black hole completely gone, leaving behind a void where once there was a massive gravitational force? To answer this, we must look at the nature of the radiation itself. Hawking radiation consists of particles that are emitted from just outside the event horizon of a black hole. These particles are created by the interaction of quantum fields in the vacuum near the event horizon. This process is not just a random fluctuation but is governed by the principles of quantum mechanics. The radiation that escapes from a black hole carries away its mass and energy, but it also contains information about the black hole's internal state. This information, according to some theories, might be encoded in the radiation, potentially solving the information paradox that has haunted physicists for decades. However, this theory is far from settled. Some physicists argue that the information lost in a black hole cannot be recovered, while others believe that the radiation emitted by a black hole could carry the key to understanding the fundamental structure of the universe. The question of whether or not information is truly lost remains one of the most profound and unresolved mysteries in modern physics. It touches on issues related to the very nature of reality and the laws that govern the cosmos. As we continue to explore the nature of black holes and Hawking radiation, we are also faced with the larger question of how these phenomena fit into our broader understanding of the universe. The study of black holes has already led to many important breakthroughs in physics, and as our theories continue to evolve, we may find that black holes are not just the remnants of dying stars but fundamental players in the grand design of the universe itself. Hawking radiation and the eventual evaporation of black holes challenge our deepest assumptions about the nature of space, time, and matter. What we do know is that the exploration of black holes and the mysteries they hold will continue to captivate the imagination of scientists and laypeople alike. The search for answers to the questions raised by Hawking's theory will shape the future of physics for years to come. Whether it's the quest for a unified theory of quantum gravity, the resolution of the information paradox, or the possibility of new universes beyond our own, the study of black holes is far from over. As we look to the stars and contemplate the nature of the universe, we are reminded that the answers to our greatest questions often lie in the most unexpected places. Black holes, once thought to be purely destructive forces, may hold the keys to some of the most profound mysteries of existence. And in the process, they may lead us to a deeper understanding of the very fabric of reality itself. As we continue our journey into the depths of black holes, one of the most intriguing aspects of Hawking radiation is the potential for new insights into the very structure of spacetime itself. According to general relativity, Spacetime is a smooth and continuous fabric that can be curved by the presence of massive objects. However, quantum mechanics suggests that on the smallest scales, spacetime might be much more granular, with tiny fluctuations that occur at the Planck scale, an incredibly small distance far beyond the reach of current technology. These quantum fluctuations could play a pivotal role in understanding the behavior of black holes and their eventual evaporation through Hawking radiation. If spacetime is indeed granular, the smooth, continuous nature described by general relativity might break down near the event horizon of a black hole. At this point, the quantum effects of gravity could become dominant, leading to a deeper understanding of the relationship between quantum mechanics and general relativity, two theories that have traditionally been at odds with each other. The discovery that black holes could gradually lose mass through Hawking radiation has profound implications for our understanding of the universe. In particular, it challenges the idea that black holes are permanent, unchanging objects. In the past, scientists thought that black holes, once formed, would continue to grow by absorbing matter and energy, with no way for them to shrink or disappear. But Hawking's theory suggests that, over incredibly long timescales, even the most massive black holes will eventually vanish, leaving behind a faint trace of their existence in the form of radiation. This raises an interesting question. If black holes eventually evaporate, does that mean they are part of a cycle of birth and death, similar to other cosmic objects like stars? Perhaps black holes are not the end state of a star's life, but rather one step in a larger, cyclical process that governs the evolution of the universe. If Hawking radiation is correct, then black holes could eventually give way to new forms of matter and energy, leaving room for new cosmic structures to emerge. The idea that black holes might not be permanent also opens up new possibilities for understanding the ultimate fate of the universe. If black holes can slowly evaporate, then it raises the possibility that the entire universe could undergo a similar process of gradual decay. In a distant future, as black holes continue to evaporate, the universe may become a cold, empty place, devoid of matter and energy. This concept ties into the heat-death theory of the universe, where all energy eventually spreads out and becomes evenly distributed, leading to a state of maximum entropy. However, the ultimate fate of the universe is still a matter of intense debate among scientists. Some theories suggest that the universe could eventually collapse in on itself in a big crunch, while others propose that it could continue to expand forever, slowly losing energy, and eventually fading into darkness. The role of black holes in these scenarios is still unclear, but they may hold the key to understanding the long-term future of the cosmos. As we continue to study black holes and Hawking radiation, we also find ourselves confronted with another question. What happens to the information that falls into a black hole? According to the laws of quantum mechanics, information can never be truly lost. However, if a black hole evaporates and disappears, does that mean the information that it contained is lost as well? This question, known as the black hole information paradox, has been one of the most vexing problems in modern physics. For years, scientists have debated whether information can escape from a black hole, or whether it is truly lost forever. In the context of Hawking radiation, the issue becomes even more complicated. If black holes emit radiation and eventually vanish, what happens to the information that once resided inside them? Some physicists have proposed that the information is not lost but is encoded in the Hawking radiation itself. In this view, the radiation emitted by a black hole could carry a record of the information that fell into it, allowing it to be recovered over time. Others have suggested that the information could be stored on the event horizon of the black hole, in a form that is only accessible under certain conditions. The holographic principle, which we mentioned earlier, is one potential way of resolving this paradox. According to this principle, all the information about a system is encoded on its boundary, rather than within its interior. In the case of a black hole, the event horizon would serve as this boundary, and the information it contains could, in theory, be preserved. But even with these theoretical developments, the question of information loss remains one of the biggest unsolved problems in physics. The resolution of the black hole information paradox would represent a major breakthrough in our understanding of quantum mechanics, gravity, and the fundamental nature of reality. Despite these challenges, the study of black holes and Hawking radiation continues to inspire new ideas and discoveries. In recent years, advancements in observational technology have allowed scientists to study the behavior of black holes in greater detail. For example, the Event Horizon Telescope (EHT) collaboration has captured the first-ever image of a black hole, providing a visual confirmation of its existence and offering a new avenue for studying their properties. The EHT's groundbreaking image of the black hole in the center of the galaxy M87 has opened up new possibilities for testing the predictions of general relativity and Hawking's theory of black hole evaporation. By observing the behavior of matter and radiation near the event horizon, scientists hope to learn more about the processes that govern black holes and their eventual fate. The image also provided evidence that black holes are not simply points of infinite density but rather have complex structures that can be studied using advanced imaging techniques. In addition to these direct observations, experiments in particle physics could also help shed light on the nature of black holes and Hawking radiation. For example, researchers are exploring the possibility of creating analog black holes in the laboratory, artificial systems that mimic the behavior of real black holes. These experiments could provide valuable insights into the properties of Hawking radiation and the dynamics of black holes in a controlled environment. One of the most promising areas of research is the study of gravitational waves. These ripples in spacetime, first detected in 2015, are produced by the acceleration of massive objects, such as the collision of two black holes. By studying the gravitational waves generated by black hole mergers, scientists can gain new insights into the nature of black holes and the role they play in the evolution of the universe. As we gather more data and refine our theories, we may eventually uncover the answers to some of the most profound questions in physics. What happens to the information that falls into a black hole? How do black holes fit into the larger cosmic picture? What is the true nature of Hawking radiation, and how can it help us unlock the secrets of the universe? These are questions that have captivated scientists for decades, and as our understanding of black holes continues to grow, we are one step closer to finding the answers. The study of black holes and Hawking radiation represents one of the most exciting frontiers in modern physics. As we explore the mysteries of these enigmatic objects, we are not just learning about the nature of black holes, but also about the fundamental workings of the universe itself. From the quest to unite quantum mechanics and general relativity to the search for a theory of quantum gravity, the study of black holes offers us a unique opportunity to deepen our understanding of space, time, and reality. As we continue to probe the depths of these cosmic giants, we can only wonder what new discoveries await us, and how they will reshape our understanding of the universe in the years to come. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.